Hello, everyone. I'm Zaiwei Chen. I recently graduated from the School of ISYE at Georgia Tech. Today, I'm going to present our work on stationary behavior of constant step size SGD type algorithms and asymptotic characterization. So this is a joint work with my colleague Shanzong Mo and my advisor, Dr. Siva Dejamagaluri, both from Georgia Tech. Okay, so let's start with motivation. So stochastic approximation algorithms, also known as stochastic iterative algorithms, are major workhorses for modern optimization and machine learning. So in general, stochastic approximation is of the following form. So xk is the iterate of interest, alpha k is the step size or learning rate. And what is in the update is some desired update plus the noise. So there are many popular examples of stochastic approximation. So for example, if my update is the minus gradient of some objective function, then in this case, this is the popular stochastic gradient descent for minimizing f. So this rises in optimization and also deep learning. So in reinforcement learning, popular algorithms such as Q-learning and TD learning can all be modeled by stochastic approximation algorithms for solving the Bellman equation. So in terms of convergence behavior, so it is well known that if we use constant step size, then let's say if we look at the mean square convergence between xk and the desired limit point x star, then the mean square convergence will converge very fast to a ball centered at the limit point x star. And the size of the ball is actually proportional to the step size. So we do not have asymptotic convergence in this case. However, the convergence to the ball is actually very fast. In order to achieve asymptotic convergence, we should use diminishing step sizes. To be specific, this non-summable but square summable step size. So in this case, we have asymptotic convergence to the point. However, the convergence rate will actually be slower compared to using constant step size. So because of that, it is actually constant step size stochastic approximation algorithms that are more preferred in practice. So in this work, we studied constant step size stochastic approximation. And as we see, as we discussed earlier, the iterate xk of alpha, xk associated with constant step size alpha, does not converge asymptotically, but has a stationary distribution. So the goal of this work is to study a centered and scaled version of such stationary distribution. So we want to categorize the stationary distribution. So why are we interested in this problem? So first of all, since in stochastic approximation, usually we want to understand like how many iterations are needed to achieve certain level of accuracy with some high probability. So by categorizing the stationary distribution, we answer this question, but actually we provide more information since we not only have the tail, but have the desired, the entire distribution. So also it can be used for new algorithm design. We can design based on this result, our next step is to design new algorithms so that the stationary distribution is better behaved in the sense that it has a smaller covariance matrix. Beyond that is actually, I mean, this problem alone is actually an interesting theoretical problem. Okay, so let me be more specific about our goal here. So this is the constant step size stochastic approximation algorithm. So as we said earlier, the iterate has a stationary distribution. It depends on the step size alpha and the noise sequence. So it's a function of both things. So however, for a fixed constant step size, it is in general not possible to fully characterize the stationary distribution. So why is that? Because every time step we're adding a constant amount of noise into the iterate. So unless we know the entire distribution of the noise, which we usually do not, it is not possible to fully characterize the stationary distribution x alpha. So this motivates us to study the asymptotic behavior. So for every fixed step size, we have a stationary distribution. If we let the constant step size go to 0, then the fixed distribution will convert to another, to another distribution, which does not depend on the whole distribution of the noise. That's the point. So to be more specific, we want to define a centered scaled version of this iterate x alpha. So this scaling function g of alpha is actually very important in this work. So this g of alpha must be chosen very carefully unless we Otherwise, we got some trivial distribution. It's either a point mass or some flat distribution. Okay, so we want to characterize the stationary distribution that's under the condition that we choose the correct scaling function. Okay, so to summarize, we define the centered scaled version of xk by yk here, and here g of alpha is the scaling function. And our goal is to first find the correct scaling function g of alpha, and then under that, we want to characterize the following two-step weak convergence. So we first let k go to infinity, and then yk of alpha converges to some y of alpha, which is different for different alpha. And then we let alpha go to 0, and then y of alpha will further converge to some y. Okay, this is analogous to the heavy traffic analysis in stochastic networks. Okay. So next, I will provide an illustrative example to further explain our goal here. So consider a simple stochastic approximation algorithm here. So in this algorithm, the update is just minus xk plus wk, where wk is the noise. And we assume the noise is IID standard normal. We will relax this assumption in later slides. So this SA algorithm can be viewed as a stochastic gradient descent for minimizing quadratic function. Okay, so if my objective function is 1/2 norm square of x, then if we do a stochastic gradient descent, then this is the algorithm. Okay, so since my noise is assumed to be IID normal, and my xk is actually just a linear combination of IID standard normal random variables, it's actually very easy to compute like all the distributions we want. So in particular, after some straightforward algebra, we have the following result. So xk of alpha itself is a Gaussian distribution with the mean and variance presented here. Okay, so if we let k go to infinity, then the mean will converge to 0, and the variance will converge to alpha divided by 2 minus alpha. Okay, so this is the stationary distribution of xk. Okay, however, in this case, we see that if we further let alpha go to 0, then this doesn't make any sense because the distribution will actually converge to a point mass. Okay. Oh, by the way, in this case, we can fully characterize the distribution for a fixed step size because of the simplicity of the update rule and the noise. If we have a more complicated update rule and the noise is not IID standard normal, then in general, we cannot categorize the distribution of x of alpha for a fixed alpha. Okay. Okay, so proceed. So if in this case, if we directly let alpha go to 0, we get some trivial thing. So in view of this, the variance term, the correct scaling in this case should be square root of alpha. So if we define the scaled iterate y of alpha by x of alpha divided by square root of alpha, then in this case, y of alpha will has a normal distribution with mean 0 and variance 1/2 minus alpha. In this case, if we further let alpha go to 0, then y of alpha will converge to y, which is a normal distribution with mean 0 and variance 1/2. So in this simple case, the stationary distribution is normal and the scaling function is square root of alpha. So we are interested in more general cases. Let's say if we have a more general update rule and the noise is, we don't know the entire distribution, probably we only know the mean and the variance. In this case, can we categorize the distribution and also can we determine the correct scaling function and also characterize the distribution? So in particular, we're interested in the following two questions. So is the scaling function always square root of alpha? So square root of alpha makes some intuitive sense because in central limit theorem type of results, the scaling function is actually also square root of k. So and also we want to see if the stationary distribution is always Gaussian. So in the next few slides, we will answer these two questions. Okay, so the stochastic approximation algorithms of interest. We're interested in three types of SA algorithms. So first is SGD for minimizing a smooth and strongly convex objective function. So this algorithm is used to minimizing f. And second, we are interested in linear stochastic approximation with a Hurwitz matrix. So A here is a matrix whose eigenvalues are in the open left half of the complex plane. So this is what means by Hurwitz. So this update equation is related to solving the equation ax plus b equal to 0. So this problem arises in many contexts. For example, in linear regression, we're essentially solving a linear equation. And also in reinforcement learning algorithms such as TD learning, the algorithm is essentially a linear stochastic approximation algorithm. So lastly, we are also interested in contracted stochastic approximation. So in this update rule here, T operator is a contraction operator with respect to some norm. So this problem is closely related to, this update equation is used to solving the fixed point equation Tx equal to x. So in fact, this type of problems also arise in the context of reinforcement learning, where the goal is to solve the Bellman equation, which is actually a fixed point equation. The assumption we're going to make is that the noise sequence is an IOD sequence with mean zero and a positive definite covariance matrix. So this is a relaxation of the previous assumption where we assume that the noise is Gaussian. So in order to apply our results to, let's say, reinforcement learning algorithms, we need to further relax the noise assumption to like Markovian. So now we assume it's IID. So that's actually a future direction. Okay. So for these three types of stochastic approximation algorithms, our goal is to find the scaling function and characterize the two-step weak convergence. So basically, we're going to answer these two questions: what's the scaling function and what's the stationary distribution of y? Okay, so for all three cases, we show that the scaling function is actually square root of alpha. So this is not very surprising because all these cases can be viewed as, to some extent, an extension of the simple case where we have the stochastic gradient descent for the norm square function in the illustrative example. And also for all three cases, we show that the distribution, the stationary distribution of y is actually a normal distribution with mean zero and a positive covariance matrix. So the covariance matrix for all these algorithms is actually a solution of some proper Lyapunov equation. So for time limit, I'm going to present only one Lyapunov equation here, which is for the SGD algorithm. So Lyapunov function for SGD, the Lyapunov equation for SGD is presented here. So the covariance of the stationary distribution is a unique solution to this, where this HF matrix is the Hessian matrix of the objective function f at x star. So since my objective function is strongly convex, this Hessian matrix is actually a positive definite matrix. This ensures that this Lyapunov equation has a unique solution. Okay, so in fact, so we don't actually show this result. We don't quite show this result. So we actually show this result under an additional uniqueness assumption here. So let me present this result in full glory. So for this SGD algorithm, actually similar for other algorithms like linear assay and contractive assay. So when the current scaling function is square root of alpha, the limiting random variable actually satisfies the following equation for all t in Rd. So this equation is actually an equation in terms of the distribution of y. So the distribution of y should be such that this equation holds for all t in Rd. Okay, so if the solution to this equation in terms of the distribution of y is unique, then we show that y obeys the desired Gaussian distribution. So this uniqueness is currently imposed as an assumption here, but we conjecture that it should hold. So this should have a unique solution. Okay, so the uniqueness assumption, we actually show this assumption in several special cases. So for example, if it's in the scalar setting where this iterate is a scalar, then in this case, we establish the uniqueness assumption. And also in the special case where the covariance matrix sigma and also this Hessian matrix F, if they're both identity matrices, then we can show the uniqueness. So for more general cases, that's actually a future direction. Okay, looking beyond, we have shown that for SGD, linear SA, and contracted SA, the scaling function is square root of alpha and the limiting distribution is Gaussian. So the question is it always the case? So surprisingly, actually, no. So in general, the scaling function need not be square root of alpha and the stationary distribution need not be Gaussian in general. So to see this, we provide a numerical simulation here. Okay, let's consider the SGD for minimizing fx equal to x to the power 4 divided by 4. So this is the SGD algorithm here. So as we see, this objective function is neither smooth nor strongly convex. Okay. Now, if the correct scaling function is square root of alpha, then if we plot the empirical density function of xk divided by square root of alpha, then we should observe convergence. However, here we do not observe convergence. So if when the step size decreases, this stationary distribution, the empirical density of the stationary distribution actually gets smaller, gets flatter and flatter. It changes drastically. It means that square root of alpha is not the correct scaling. However, if we plot the empirical density function as a function of alpha to the power 1/4, okay? So in this case, we observe convergence. When the step size goes to 0, it actually converges. All these distributions actually converges. So this means that alpha to the power 1/4 is the correct scaling function. To further characterize the stationary distribution, we plot the log of the empirical density function as a function of y to the power 4. Okay, so in this case, we observe straight lines. This means that this density function should be proportional to e to the power beta y to the power 4, where beta is some constant. So this means that the stationary distribution is actually not Gaussian, it's some general Gibbs distribution. So in our paper, we actually provide a heuristic approach to find the correct scaling function. However, to further characterize the distribution is much more challenging and is a future direction. Okay, so to conclude, in this work, we focus on constant step size stochastic approximation algorithms. In particular, we show that for SGD with a smooth and strongly convex objective and linear SA and contractive SA, the correct scaling function is square root of alpha, and the limiting distribution is a Gaussian, with mean 0 and covariance matrix being the unique solution of some proper Lyapunov equation. For more general stochastic approximation algorithms, we show that the scaling function need not be square root of alpha, and the limiting distribution need not be Gaussian. So further characterizing the stationary distribution in these cases is a future direction of this work. So thank you all for listening. Let me know if you have any questions.